So this is teaching 00 and we are talking about concepts and terminology. Alright, in our interactive teaching session we've been setting up and exploring SuperCollider, and we've seen that SuperCollider is an integrated computer music system consisting of an IDE which contains an editor. This editor allows us to enter code within the SuperCollider language. We also have an interactive help system on the right side which we can use to explore the functionality of SuperCollider. And of course we've got an output. As SuperCollider is a client-server system, we need to start a server which is then generating the sound and is using the definitions that we write within our editor in the computing language of SuperCollider. Now we've been exploring the stuff and learned some central commands. So in order to start the server, we can just press Ctrl B and the server is going to start, and in the lower right side we will see the status of the server and the status of the interpreter, namely the language. And we can then enter some code, some SuperCollider code, and are able to evaluate it either by putting the cursor at the end of a line and press Ctrl Enter, or evaluating a whole block which is embraced in standard brackets. Again, we press Ctrl Enter and the code will be evaluated, and depending on the results there's going to be some output in our post window. Now, once sound is produced, you may stop the sound just by pressing Ctrl dot, and in order to navigate to the relevant information in the documentation, you might place the cursor on some word that you entered into the editor, and then just press Ctrl D for definition, and then the documentation is going to be searched for the relevant expressions. Now, another way to interact with the IDE is to click on the right lower left, namely here where the green letters are written. Then there's going to be a pop-up window, and the pop-up window gives us a couple of possibilities in order to inspect the server, the status of the server, and inspect the sound generation. So for example, there is the possibility to have a couple of displays, an oscilloscope, a frequency analysis. We can also have a look at the internal node tree to have an understanding how the memory is currently used, and we can also show the meter which shows us the input-output loudness. We might be starting recording the output of SuperCollider. An appropriate file will be created within the document directory of your computer. And obviously we can control the loudness of the system, so we can mute it, or we can define the volume by just using the slider. The meters I just showed, I'm showing here 4 of the meters. We can see the stethoscope, the oscilloscope, we can see the time representation of the signal, but we can also see the frequency representation here of the very same signal, and as you can see we can identify the basic fundamental frequency, but also the distribution of the harmonics. Here on the left side we see the node tree, and as you can see there's a single synthesizer, SynthDev, which is running right now, which is an FM synthesizer, and this is producing this signal. And here on the right side we see the meters. So as you can see, there is input very low level. This is just my microphone which is added. On the output we see the loudness of this signal that is going to be produced. Now, a central terminology and a central concept of music is an oscillation, periodic oscillation. I just created a number of plots of a sine wave. Again, the code here may be entered into SuperCollider, and in order to show the three most important terminology words that might be that we are going to use within computer music, namely, which is frequency. Frequency defines the number of repetition of a full period of in a second of an oscillation, and the unit that is going to be used there is hertz or hertz. So we are counting the number of repetition of a full period. The second part is the amplitude, and the amplitude is basically the maximum extent of the oscillation with respect to the equilibrium. In our case, this is 0, and in our case the values should be in the range of -1 to 1 for the amplitude. And the final important concept is the phase, and which is very loosely the shift of the wave cycle on the x-axis, so on the time. So we're shifting it to the left or to the right, and this is normally defined as the angle between 0 and 2 pi. Now, what exactly does this mean? In audio terms, where the frequency basically denotes the perceived pitch of the oscillation. The higher the frequency, the higher the pitch. And for example, if we've got a frequency of 440 hertz, which means 440 periodic cycles per second. This denotes the Kammerton, as we say in German, or in English, the standard pitch for the A1 or das eingestrichene A, which should be, I'm not quite sure, but I think it's A1 also in American terms. Now, with respect to the amplitude defines how loud a sound is perceived. Amplitude will often be specified using decibel, which is a relative unit, but which can also be translated into an absolute value. Okay, now static phase shifting of an oscillation usually cannot be perceived, so you don't hear that. But once you overlay multiple sounds and they have phase shifts, this may lead to clearly audible artifacts. For example, they might be killing the sound up to complete silence. And just as a simple notice, when you're modulating the phase, that is, you're changing it over time, then audible artifacts will occur, and this is the base for a very powerful synthesis approach, which we will have a look at later in the course. All right, this is the code that you can use for experimenting with frequency, amplitude, and phase of a sine wave, and try it out in SuperCollider. All right. We also had a look at modular synthesizers, specifically in order to understand how electronic music has been created over the last 6-7 decades. And as you can see, the idea of a modular synthesizer is to have small modules that will be connected via patch cables. And these patch cables route the current from one from one module to the other, and the complexer, you can kind of set up a very complex settings with these patch cable approach. Now, the concept that is behind that has been kind of like mimicked in the case of digital computing, and actually it's the other way around, because the modular synthesis came after the unit generator approach. So the unit generator approach are the basic formal units in most of the so-called music and style computer music programming languages. And the very first one has been defined by Max Matthews with his colleagues at the Bell Labs in the 1950s, which is before the modular synthesizers have come alive. And the unit generator form a building block for designing synthesis and signal processing algorithms. So basically, they are conceptually the same thing as a module, and data is routed into the UGen and out of the UGen. All right. And Super Collider, just like Pure Data and MaxMSP, for example, belong to these kind of languages, to this type of languages, which are now denoted music and style computer music programming languages. So now, when modules or UGens are interconnected, then it becomes possible to change parameters of the UGens. So in electronic music, we say that we want to modulate something. This doesn't refer to the module as a physical object or UGen. It's a modulation, and the modulation basically means change, and very specifically a continuous or cyclical change over time caused by one signal to control another. So we've got two units, two unit generators, and the one is controlling one parameter or more parameters of the other. And the controlling signal is known to be the modulator because it controls some specific property of the sound that we are listening to. And the sound is generated by another unit generator, and as it's carrying the sound, it's called the carrier. So modulator controls property of the carrier. And once you've understood this very simple concept, you can basically combine everything with everything. Okay, so for example, if we have a look at the architecture of a subtractive synth, it looks like this. We haven't talked about that in the lecture, but we can see that there are modules like the VCO, like the VCF, like the VCA, or like UGens, like an oscillator, a filter, and an amplifier. And as you can see, there are other modules, other UGens, like a low frequency oscillator that controls, for example, the frequency of the other oscillator, or might be controlling the amplitude, or might be controlling the phase. So here we've got an oscillator, and the second type of modulator that is very common is a so-called envelope generator, and these envelope generators are basically function generators. They generate a function over time, and they might control the filter or might control the amplitude. So, and a very common envelope generator is a four-phase function generator called ADSR. It goes from 0 to 1, then it decays, then it stays at a certain level, and once the key is released, then after some time it goes back to 0. So we get this kind of function, and these can easily be created in Super Collider. There are lots of function generators or envelope generators, and here's the ADSR. As you can see, it goes up and it goes decays, and then it will stay at a certain level at some time, and then eventually it's going to fade away. And these are the parameters that you can use there. There are other envelope generators like percussions, which go up very steeply and then very quickly go down to 0 again without any decay phase or anything. There's no sustain. All right, so and the last possibility that we've been talking about is to modulate, to change sound using randomness. So the concept is aleatoric music, and we can find this in music, art, and literature, and it refers to the use of a non-systematic operations. So these are functions, but there might be non-systematic operations that lead to an unpredictable and, into a large scale, random outcome. So the outcome of the function might be randomness. So in analog systems, we have, by their very design, they always exhibit a random behavior. If they are getting warm, then probably the frequency might change. They've got some noise, which they just generate, and therefore they have got this random behavior, which makes them sound in a very specific way, which people like. Now, digital systems usually don't carry any random behavior. They shouldn't. They should be very, very controlled, but they will be able to, or are capable of so-called pseudo-random behavior. That is, they are providing us with functions that create data which is behaving like random data to a certain extent, but are not real random data. Anyway, the pseudo-random behavior is random enough to create interesting musical effects. Right, so let's try to conclude what we've learned in our first session. We started Super Collider and experimented with the language, with the server and with the help system, and gained some insight how to use the system, created some first sound. Then we talked about central concepts and terminology of computer music. The central term is, of course, UGen, the unit generator. Then we've learned a little bit about modulation. We've seen oscillators, and we talked about amplitude, frequency, and phase. And we also have talked a little bit about envelope generators and randomness. Okay, so far for the first teaching session about concepts and terminology.